I would like to talk about the expected difference between the Nielsen number and the minimum number of fixed points. This is a project that Sungwon Kim and I have been working on things related to this for some years now. I think it's an interesting problem. This is something that was mentioned a couple times yesterday, the famous theorem by Beckon. If x is a manifold of dimension not equal to 2, then the Nielsen number is equal to the minimum number of fixed points. This is kind of the whole point of the Nielsen number. What about surfaces when the dimension is 2? I thought we should start with a quotation from a famous mathematician to begin the talk. This is from Ulrich Koschork. Actually, yesterday, this is a quotation from 2016. He said, in dimension 2, the beckon theorem, I wrote this down when he said this, the beckon theorem is very badly wrong. In dimension 2, the Nielsen number is not equal to the minimum number of fixed points. Very badly wrong. So this talk is actually, I think we all agree that it is wrong. It's not this equality here. Nielsen number is actually not equal. But I would like to talk about very badly. Is it really very badly wrong or simply just wrong? That's what I would like to talk about. So I want to try to measure how badly wrong is it? Is the situation on surfaces? I'm going to focus on surfaces with boundary, although all of these questions you could also ask for surfaces without boundary. It's just, it is harder in that case, and we haven't really done anything in that setting. So the example, or what Ulrich mentioned this, Mike Kelly showed that the minimum number and the Nielsen number can be very far apart, arbitrarily large. And specifically, actually, here's the example that Mike came up with in his paper. So when I describe functions in this talk, I'm going to just give you the induced homomorphism. And in Mike's case, he was looking at the pants surface, and the fundamental group is a free group of 2 generators, which are called A and B. And this is his example here. So A goes to this complicated thing, where K here can be any integer, and B just goes to the trivial element. And Kelly does a computation, and he shows that the Nielsen number for such a map is 0, but the minimum number is equal to 2K, and this K here can be anything. And so that means that the minimum number can be as large as you like, and the Nielsen number is still just equal to 0. So that means this difference here can be arbitrarily large. So the big question which I wanted to talk about today, and like I said, always in the case of surfaces with boundary, when the Nielsen number is not equal to the minimum number, or even in cases like Mike's example, when the Nielsen number is much less than the minimum number, is this kind of behavior a typical behavior, or is it exceptional behavior? So should we expect this to happen usually, or almost never? That's the question I want to ask. More technically, or maybe less technically, if I choose F to be a map sort of at random on a surface with boundary, should I expect it to be beckon? That is, should I expect the Nielsen number to equal the minimum number? Or you could also ask this, if you choose the map at random, what is our sort of statistical, the expectation for this quantity, the minimum number minus the Nielsen number, the expected value of this quantity? Statistically, could we measure that? These are the kinds of things I want to talk about today. So let's talk about, the obvious question is, what does this mean when you choose at random? How do we formulate the randomness? And that, hopefully, we also need to talk about what this means, but hopefully we can do both in the same way. So to measure random things, we're talking about homomorphisms on free groups. So we're always going to measure this randomly, the randomness in terms of homotopy classes of maps. Of course, everything from the Nielsen theory is homotopy equivalent. So if we are talking about a bouquet of circles, I said surface with boundary, but these are homotopy type of bouquet of circles. And the fundamental groups are free groups on n generators. This, by the way, this is why I'm focusing on surface with boundary, because it's a free group. If it's without boundary, it's a more complicated group. Not much more, but enough more to ruin my techniques here. So we have a free group on n generators. I'm going to write it this way. G means that group, and N will be more or less fixed for the whole time. And the generators I'll write this way, A1 to AN. Now, we can measure the size of a subset of this group using something called the asymptotic density. This is something that's been around for quite a long time. People have been using this in number theory for a long time, and more recently in group theory. So let's talk about the asymptotic density. For a natural number p, I'm going to let GP be the set of elements of G with word length at most p. You know, in a free group, you can classify the elements by their reduced word length. And so GP means all the elements of length less than or equal to p. And you can define this. I'll call this D sub p of S. It's the number of things of length p in S divided by all the things of length p. And this is the proportion of things of length p which are in S. And you can think of this as the probability. If you choose a random word of length p, this is the probability that it is in S. This is not asymptotic yet, but if I then consider the limit when p gets arbitrarily large, this is the definition of the asymptotic density. So you take these are all finite proportions, and you take the limit as the p goes to infinity. This is the asymptotic density of S. And this you can do for subsets. All right, sometimes actually this limit here may not exist. Which is a bit of a technical difficulty sometimes. So in those cases, if I just don't want to worry about if the limit exists or not, we can also define these two densities. This is called the lower density and the upper density. And these ones always exist because these dp's are ratios. They're between 0 and 1. And so those two quantities will always exist. Usually, actually, I will be discussing these two because I don't want to have to prove that the limits exist. These are easy enough to talk about. All right, when the density equals 1, we say the set is called generic. And like I said, the densities represent the probability that a random element of the group is in your set S. And the randomness you should think informally as being random for very long ones. It may not be considering the short words, but when the words are very long, because of this limit here. All right, so this is how we're going to measure these probabilities that I was talking about, probabilities for properties of random elements. I was talking about only elements. What about homomorphisms? Because this is what I really want to talk about is if you choose a map at random, then what are the properties you expect? So what about homomorphisms? Well, a homomorphism, like I wrote before, I'm going to write examples of homomorphisms. They look something like this. This is for the group on 3 generators. If you want to choose a homomorphism, it's equivalent to simply choosing these 3 words. These are the images of the 3 generators. And so a homomorphism is equivalent to the n tuple of the image words, the image of each generator. So in this case, this is 3 words that you have to choose to make a homomorphism on the group of 3 generators. So combinatorially, what we're talking about, the set of endomorphisms, G to G, is actually just G to the power n, the product of G n times. And then we can just define the density this way. So if S, this time S is not a set of elements, but a set of homomorphisms. And we can define the density just like we did before. So this GPN means the nth product of GP with itself. And also we're going to define the lower and the upper densities so that we don't need to worry about convergence of the limit. All right, so these probabilities, or these numbers, the densities represent the probability that some random long homomorphism is in S. And by long homomorphism, I mean one in which when you write out the image words, they're all very long. All right? Now, one thing about random homomorphisms has been known for some time. It wasn't described in these words, but in Wagner's original paper about remnants and Wagner's algorithm, Bob mentioned this yesterday. Bob and Wagner showed that the density of the homomorphisms with remnant equals 1. I think he mentioned this. Almost all homomorphisms have remnant in this sense. And I'm going to talk a little bit later about what exactly the remnant means, but the remnant was important in their work. All right, usually these sets of homomorphisms, of course, we only care about homomorphisms because they represent induced homomorphisms of continuous functions on the bouquets of circles, continuous maps. So I'm going to sometimes write this Nielsen number of a homomorphism. This just means the Nielsen number of some continuous map whose induced homomorphism is phi. And because this is a k pi 1, there's no ambiguity. You can just talk about the Nielsen number of the homomorphism as if you were talking about the original continuous map. And similarly, the minimum number of fixed points of a homomorphism, this actually is not related to the fixed subgroup of this homomorphism. This just means the minimum number of fixed points of some continuous map whose induced homomorphism is phi. And here's a simple result, just to give you a feeling for what we're going to try to talk about. Let's let N1 be the set of homomorphisms which have Nielsen number greater or equal to 1. So this is sort of considering all the maps which have Nielsen number 1 or more. Right? So the density of such a set would represent the probability that a random map has Nielsen number at least 1. Right? Of course, not all maps have Nielsen number 1 or more, but well, it's not hard actually to show this density equals 1. That means if you choose a random map on a bouquet of circles, you expect the Nielsen number to be at least 1, probably much more than 1 actually. If you choose a random homomorphism and write it out, the words will be very long. You expect it to have a lot of fixed points actually, and probably they're not all going to cancel out, so probably the Nielsen number will be large. So almost all maps have Nielsen number at least 1. In fact, Sungwon and I in an earlier paper showed that if you take not just the Nielsen number 1 or more, if you take nk means the ones which have Nielsen number greater or equal to k, then this also is density 1 for any k, no matter what the k is. So even if you want to consider all the maps which have Nielsen number greater than 1 million, that still is density 1. So if you choose a map at random, you actually expect the Nielsen number to be very, very large. Greater than any fixed amount is what your expectation should be. That's what I just said. For any fixed k, a random homomorphism will have Nielsen number greater than k with probability 1. So you could say informally, almost all maps have Nielsen number arbitrarily large. Really what I'm talking about here is I'm trying to get at this idea of expectation, which I said at the beginning. So another way to describe this in terms of the expectation, this is like the statistical expected value. Probabilistically, we should say the expected value of the Nielsen number is infinity. It doesn't mean that a random map has infinite Nielsen number. It means that if you choose a map at random, you should expect the Nielsen number to be very, very large. Generally, this is going to be the definition of the expectation that I'm going to use. So if f is a real valued function, up here I was talking about the Nielsen number. Nielsen number is an integer, but it doesn't have to be an integer. If f is any real valued function of homomorphisms, the expectation of f is defined in this way. This is the same way you would define this is the average of all the possible maps of length p. You add up all their values, you divide by the number of such maps, and you take the limit. That makes it an asymptotic expectation. All right? And then similarly, we define these lower and upper for the same reason, because the limit might not exist, the lower and upper expectations. So this is how we're going to discuss the expected values. All right? So I just said the expected value of the Nielsen number is infinity. Also, the expected value of the minimum number, because the minimum number is greater than the Nielsen number, this is automatically also infinite. I think, by the way, this is just when I was writing the talk, I thought about this. I think if you take the Lefschetz number, I think this expectation is actually 0, because the Lefschetz number can be positive or negative. And anytime you have a positive Lefschetz number, there's also the same homomorphism, really, that gives you the negative Lefschetz number if you invert everything. So if you are doing this sum here, adding up all the Lefschetz numbers, you expect them to cancel out in pairs. So I think you'll get 0 here. This is maybe more interesting, if any of this is interesting at all. If you take the absolute value of the Lefschetz numbers, I don't know about that, because then they won't cancel each other out. Maybe this is infinite. Although I think the individual ones may be close to 0, because I don't know. Anyway, the goals for the rest of my time, really what I want to talk about is what is the expectation for this difference here, the minimum number minus the Nielsen number. Is it infinity? If it's infinity, this is really very bad news for Beckon's theorem. It means that usually we expect the minimum number to be very different from the Nielsen number. So this is what I want to compute, the expectation of the minimum minus the Nielsen number. I'm also going to consider this. This is another way that you could try to compare. This would be comparing the actual values of the minimum and the Nielsen number. This would be, as a ratio, the Nielsen number compared to the minimum number of fixed points. I would say the best result possible in terms of Beckon's theorem, if you want the Beckon theorem to be true as possible, the best result would be the expectation of this would be 0, and the expectation of the ratio would be 1. This would mean in kind of two different ways. We expect the minimum number and the Nielsen number to be actually the same or close together at least. This would be the best in the sense of Beckon's theorem. Here's a little footnote. Actually, if you can prove this one, that automatically implies the second one. That's because you can do something with taking logs. So if you expect the minimum number and the Nielsen number, the expectation of the difference to be 0, then you can take the logs of everything or move this around and then take the log on both sides. That means the log of the minimum number should be expected to be the log of the Nielsen number. But then you can move it around again and write it this way. And so that would mean you should expect the Nielsen divided by the minimum numbers is 1. So actually, this is the stronger result, that the expectation of the difference is 0. So we're going to try to show that this is 0. And if that doesn't work for some reason, we can try this one, which I guess might be easier. And actually, I don't want to give away the ending, but this is what's going to happen. This one actually turns out to be quite a bit more difficult than this one. All right, so some past work, just to give you a little review of what we've been doing in the past. We first dealt with just a simpler question, just what is the probability that they are equal? Towards that end, we talk about this set. Wn means the set of phi where they are equal. These are the beckon. They have the beckon property. And let's compute the density of Wn. That's the probability that they are equal. The n, remember, refers to the number of generators in the group. And it turns out, I'm talking about the n here, because this density actually does depend on n. It's different for different values of n. The main tool which we're going to use for telling if f has this beckon property or not is Wagners algorithm, which Bob mentioned. I'm going to mention it a little bit more. Briefly speaking, here's how you do Wagners algorithm. I'm just going to talk about this example. Look at this homomorphism here. It's the same one I wrote before, actually. First of all, we need to talk about the remnant. So this is Wagner's definition of the remnant. Is the middle subword in each position that doesn't cancel in any product. What I mean is you take these three words here, you multiply them together, and you also multiply them together with their inverses, and you see what you can cancel on the ends of these words. In this case, in this example, this first b, for instance, you can cancel by multiplying this by the inverse of this on the left. The b will cancel. But you can't cancel the second b. The first b here will cancel, but the second b will not, and actually there's no other product which can cancel the second b. So the second b is part of the remnant. And similarly, you can just check. It's easy to check which ones will cancel and which ones will not. I put this underline under the ones which never cancel. Those are the remnant subwords. And Wagner's algorithm, it works when there is a remnant. So it can be that one of these words will completely cancel, and then there's no remnant, and you can't use Wagner's algorithm. All right, here's the theorem that Wagner proved. If phi has non-trivial remnant in each generator, then it is the induced homomorphism for a map on the bouquet of circles, and that map has these properties. First of all, this map has a fixed point for each occurrence of AI or AI inverse inside of phi of AI, and the fixed point classes. So this tells you what are the fixed points. This one tells you what are the fixed point classes. The fixed point classes are determined by the equalities among what are called the Wagner tails. And I'll just show you this example here. All right. The first thing said f has a fixed point for every occurrence of AI inside of phi of AI. So that means inside of A, I am looking here for occurrences of A or A inverse. And I see one occurrence of A. That corresponds to one fixed point. And the Wagner tails are simply the words which come before the A and the word which comes after the A. So it's very simple to do. Before the A is B squared, after the A is C. All right? And you can do this in each of the letters. Inside of phi of B, we have this B here. And it gives me another fixed point. And the two Wagner tails are the word before, which is C squared, and the word after, CA to the minus 2. Inside of phi of C, we have two of them. Actually, there's two C's in there. They give me two different fixed points. and they have different Wagner tails. The first one is BA and CA inverse, and the other one is that. This is a technicality. In Wagner's algorithm, you always, for free, you get another fixed point, which has a trivial Wagner tail. This corresponds to the wedge point in the bouquet of circles. And what I said, the second part of the theorem, the equalities between fixed point classes are determined entirely by equalities among the Wagner tails. And if you look at all of these words here, you will see none of them are the same as each other. And that means none of these are in the same fixed point classes. This is because of Wagner's algorithm. If none of these are the same, then they are all in different fixed point classes. And that means the Nielsen number here is 5, because I had 1, 2, 3, 4, 5 fixed points. And they're all different.
Did you consider the inverses of the Wagner bars too?
Well, yeah, this is actually a simple example where the letters which are occurring inside are just A here. If it was an A inverse, you need to modify this slightly. Okay. But I made my example trying to fool you a little bit into, it's slightly more complicated than I'm leading on here, but it doesn't really matter for our case. All right, so the Nielsen number is 5 here. Actually, in this example, also the minimum number of fixed points is 5, because I just said we have 5 fixed points and they're all in different fixed point classes. So not only is the Nielsen number 5, we have 5 fixed point classes of 1 point each. They're all essential. I didn't say that, but Wagner's algorithm also tells you how to tell if they're essential or not. And in this case, they are all essential. So it's a simple fact. If there are no equalities between the Wagner tails, which is the example I just said has this property, then the number of fixed points in Wagner's algorithm is equal to the Nielsen number. And also, that number of fixed points is equal to the minimum number. And so this is very simple if you understand Wagner's algorithm. If there are no equalities between the Wagner tails, then the map is beckon, because this number is equal to the Nielsen number and also the minimum number. This actually is something we should be able to count combinatorially. What is the probability if I give you one of these, something like this at random? What is the probability all these words are different? It's not simple, but it sounds possible, I guess. This actually led to a project I did with my students. You may, if you came to Beijing 5 years ago, you probably met. This is Allison here. I thought maybe I would give you a little update. Allison just got her PhD in mathematics. She does knot theory, knots and graphs. So good job, Allison. This is Jackie Brimley. She works for a financial insurance company near New York City. So she probably makes more money than me now. And also, this Grisser is Matt. He's back here. That's Matt Grisser. He works in software, so he probably also makes more money now. This was the project that we worked on, and we showed that this Wn is the beckon property maps. We showed that actually the density is greater than 0 for all n. That is, the probability that the map has the beckon property is non-zero. And this probability is increasing in n. So as n gets larger, it is more and more likely that the map has the beckon property. All right? So this is what I said. The result was, for each n, there is at least some positive probability that a random map is beckon. And this was nice. We actually improved this quite a bit, Sungwon and I. This says 2016. Actually, this paper was written in maybe 2013, but it took forever to be refereed and still hasn't appeared, hopefully, in 2016. Anyway, we showed that actually this limit, I said it's increasing in n, actually the density approaches 1 in n. So when the n is very large, you should expect almost every map has the beckon property. And this, I think, was interesting. And we stated as an open question in this paper, is it actually equal to 1 for each n? That would be certainly a better result than this. And in the case n equals 2, at least, the answer is no. And this is a new result, actually. Here is the theorem. In the case n equals 2, it is not 1. It is actually less than this. So maybe close to 1, but not exactly 1. 0.99997. This upper bound here could be improved a bit by probably not a lot, although I'm not sure. We didn't try really to optimize the bound. Our proof used some work from Wagner's other paper. Is a little known fact. Wagner wrote 2 papers, and the other one has to do with beckon property. She looked at a class of homomorphisms that Mike defined called T3. Do you remember what T3 is? No. I don't really either, but it's a very specific class of homomorphisms called T3, and Wagner proved that everything in this class is not beckon. And that class actually, we can prove, it's not hard actually to compute the density. The density is greater than this very small number, which gives this bound above here. This is the complementary. So these ones are all not beckon, so the ones which are beckon must be less than that. I think actually this is the smallest number I've ever included in a talk. So congratulations to me. I know Phil likes very big numbers in his talks. Yeah, this is a very, very small number. Okay, this argument is only for the case of 2 generators, and it relies fundamentally on Kelly's special techniques to compute the minimum number on the pan surface. So this, I don't expect to be able to generalize this, at least not easily, to higher values of n.
I'll give you some suggestions.
Yeah, okay, great. I don't think the techniques will generalize, but I do think that the result will still hold. So Sungwon and I both, I think we agree about this. We do believe that probably this density is going to be less than 1, even for greater values of n. There doesn't seem to be anything really special about the n equals 2 case. It's just that's where the most techniques have been developed. This would mean actually that the density, we already proved that the density is greater than 0. So this means the densities of beckon maps is actually strictly between 0 and 1, which would be interesting. Usually when you create examples or you try to measure densities of things in the real world, they tend to be either 0 or 1. Ones which are in between are interesting. I actually didn't expect this to be true. For n equals 2, it has to be between 0 and 1. In the case n equals 2, the best bounds we have derived is this. We know it must be greater than 0.5 and less than this number. So there's some opportunity to improve this bound. Certainly it's pretty far apart right now. Anyway, let's talk about the expectations. So I want to discuss the difference and the ratio, the expected values of those. Probably these will depend on n based on what we've been talking about. So I'm going to write them this way. E sub n means the expectation when we have n generators. All right, like I said before, the best case scenario would be that this difference, the expected value is 0 and the ratio of the expectation is 1 for all n. Actually, it's not hard to see because of this, the fact that the density of the beckon maps is less than 1, you can easily show that this expectation is greater than 0. And here, I don't know if you're interested, but it's a simple argument. So the expectation is greater than 0 when n equals 2. This is the definition of the expectation. What did I do here? Here, I have taken, instead of the sum over all homomorphisms here, I'm taking the ones which are only in the complement of W2. That would be the non-beckon ones. And this is greater because this is a smaller set. If it's in W2, it's not beckon. That means the minimum number minus the Nielsen number is at least 1. And so this is bigger than this sum. But this, you're adding 1 here. This is just the number of things in that set. And then this is the definition of the density of this set. So the expectation of the difference is greater than the density, and this density is more than that very small number. So the expectation is also more than that very small number. All right. So actually, we expect this. I just proved it for n equals 2, but I expect this is true for each n. They're probably small numbers, but they're not 0. All right. We've tried many times, Sungwon and I, to prove that these numbers are finite. These expectations, in theory, they could be infinite. I do not expect that to be the case, but it's turned out to be harder than we expected to prove that these expectations are finite. The combinatorics is very difficult. So, like I said before, we're going to instead look at this ratio. It turns out the ratio is a little easier to handle. Remember, we want the ratio to be 1, the expectation of the ratio. So here's our basic approach. Remember, we said this already. If there are no equalities between the Wagner tails, then the map is beckon. To look at the ratio here, I want to consider some cases when there are some equalities, right? there are some equalities between the Wagner tails. I want some condition which lets us predict when a Wagner tail will be repeated. By that I mean the Wagner tail equalities mean you see the same word 2 times in that big list. So when can we predict when one of the Wagner tails will be repeated? All right, here's a necessary condition. This is also a simple observation. A repeated Wagner tail must be completely outside of the remnant subword. It's simple. If W is a repeated Wagner tail, remember the Wagner tails are the words on the ends in front of the letter and after the letter, all right? If it's repeated, that means you get this same W 2 times in 2 different words. Something like this. It doesn't have to be exactly this. It could be on the other side, but something like this must be true. That the same word appears at the beginning of 2 different of these, or maybe on the beginning and on the end. Anyway, this automatically means, if you were to take the product of these with an inverse, that the W would cancel, and so the W cannot be part of the remnant. The remnant must be part of the rest of it. So this W will cancel in this product, so it is outside of the remnant. So a repeated Wagner tail must be completely outside of the remnant subword. In terms of the fixed point theory, the Wagner tails outside the remnant may combine or cancel with one another. In terms of the fixed points, they might cancel. But the ones inside the remnant can never cancel or combine with one another. All right? What this means is the Nielsen number and the minimum number are both bounded between the number of Wagner tails inside the remnant and the total number of Wagner tails. Because the only ones which can cancel or combine are the ones outside of the remnant. So the Nielsen number and the minimum number have to be between these 2 quantities. The total number of Wagner tails and the ones which are inside the remnant. All right, this is what I just said. And this means, if you want to consider the ratio, the biggest possible for the Nielsen number is the Wagner tails inside the remnant. The Nielsen number is greater than the Wagner tails inside the remnant, right? And the minimum number is less than the total number of Wagner tails. So this is a bound for the ratio of the Nielsen number. All right? The right side, you can consider this is just the proportion of those Wagner tails which are inside the remnant. All right? We have all possible Wagner tails, and we're the quotient with just the ones inside the remnant. Okay? So we can use this to estimate the ratio actually without looking very specifically at our map. In this old example here, now we already know this one, the ratio was actually equal to 1. But even if you don't look very carefully, you can estimate the ratio. Here, I have highlighted where the Wagner tails appear, right? This A, this B, and then these 2 C's, they each create different Wagner tails, all right? But you can see they are all inside the remnant. So we have 4 Wagner tails inside the remnant and 5 total Wagner tails, this is including that extra one, the trivial one. And so you can say, even without looking at very much at all here, you can just say the Nielsen number, the ratio is greater than 4/5. The Wagner tails inside the remnant divided by the total number. This is very rough. You don't have to pay attention very much to anything inside those words. All right? Now, if I want to show that this is approximately 1, then in order to make this happen, really we would like these remnant words to be as large as possible. If you want all of these things to occur inside the remnant, the proportion of the ones which are inside the remnant, you want like these little lines here to be very long. They should occupy as much of the word as possible. Everybody knows, because Bob said so yesterday, the remnant property is generic. But actually, you can say much stronger things than just any random map should have a remnant. You can say more. Based on some work, this is work in combinatorial group theory, which is pretty fancy group theory stuff. You can show this actually. For any r less than 1, so think of this as a number which is very slightly less than 1, close to 1 but less. R sub r, I'm going to call the set of homomorphisms where the size of the remnant, these bars means the word length. The length of the remnant is more than r times the length of the whole word. So if you could think of r as being like 99%, this means the remnant occupies more than 99% of the whole word. All right? I call these the maps with remnant ratio r, and it's not so hard to prove, certainly if you use this fancy group theory stuff. The maps of remnant ratio r is density 1 for any r. So you can consider any ratio arbitrarily close to 1, and you should expect that the remnants are greater, longer than that ratio of the total length of the words. All right. So this is what I said. We should expect that for any R, the remnant occupies proportion, at least R, of the image words. Really what we want to talk about is the proportion of the Wagner tails which occur inside of the remnant. But we should also expect proportion R of the Wagner tails to occur inside the remnant, provided that the Wagner tails are uniformly distributed among the image words. And I'll say a little what I mean by that. We need to make sure, for example, the Wagner tails do not cluster together or have any bias in their locations. For instance, if the Wagner tails always appeared at the very beginning of the word, you might expect them to be outside of the remnant. But if they're distributed evenly throughout the word, you should expect most of them to occur inside of the remnant because the remnant is extremely long. All right. Where do they come from? Remember the Wagner tail, we get one for each appearance of AI or AI inverse inside of phi of AI. And if phi AI is a long random word, actually we should expect these letters to be uniformly distributed inside of these words. If you choose a word at random, there is no reason that these should be clustered towards the beginning or anywhere else. They should be distributed uniformly throughout a random word. In particular, if W is a random word of length P, you can even predict how many you should expect to see. It should be roughly P over N occurrences of this letter distributed evenly throughout the word. So I want to try and prove something which indicates this. All right? It's a little tricky. We're going to use some basic probability, which is not, I have very weak background in statistics and probability, so I hope you do too. And you won't notice if I make a mistake. This, just a notation, this number AI in W, this just means the number of AI or AI inverse in the word W. If, like I said before, if we choose W completely at random, we should expect this number to be 1 over n times the length of W because each letter has equal probability and there are n different choices. Here's the result, technically what we can prove. So let S sub epsilon be the set of words which have this property. I said if you choose at random, you expect this to equal 1 over n times W. I'm going to let S be the ones where the number of AIs is greater than this, 1 minus epsilon over n times the length of W. We should expect this to be usually true, all right? And in fact, we want to prove that this density actually equals 1 for any epsilon less than W. So the probability that there are the expected number of AIs, at least that many, all right? It's interesting, I think this result is kind of interesting in its own right, just algebraically, but as far as I know, this hasn't been shown. I have a colleague who knows a lot about combinatorial group theory, and he told me that he's never heard of this, so that's good enough for me. The proof, like I said, some basic probability, we're going to count the complementary set. So I would like to know, really this is about, if you choose a word at random, how many times are you going to see a specific letter? Well, when the word has length P, the word, we expect to have K occurrences of the specific letter with this probability. This is the binomial coefficient. So you need to, if you have P positions totally, you choose K of them, which are going to be this letter AI. They will be AI with this probability, 1 over n. There's K of them, so we take the power K. And then the rest of them, we are restricting to not be AI, so they are not AI with this probability. And then the probability, this is the probability that the word has exactly K occurrences. The probability that it has less than or equal to K occurrences is this sum. You just take this and you sum starting with the K, starting at 0 and going up to whatever the K is. All right? But this actually, if you know more about statistics than me, this should look familiar to you. This is the tail end of the binomial distribution. The cumulative something or other is what they call it. This is the tail, one side of the binomial distribution. And you know some probability theory. This, in the limit, this approaches the normal distribution. And then you can estimate one side of the normal distribution by some fancy theorems. And in particular, this, when the k is small enough, that is, if the k, if you think of the normal distribution, if the k is slightly to the left of the middle, then you can estimate this using an exponential function. All right? And so the probability that there are fewer than k is bounded above by this exponential function. All right? Now, what I was looking at specifically was this probability, the probability that it's less than this quantity here, this is in the statement of my little theorem, it means this same exponential bound means that this thing is bounded above. This is not the same c, but what I care about is this length of w there is in place of the k. And then as the length goes to infinity, this exponential bound goes to 0. And so we can say this one, the complementary probability is 1. All right? The probability that's less than this is 0, so this is 1. All right? So generically, we expect this number to be greater than 1 minus epsilon over n times the length. This is for any epsilon. All right? This just tells you that the number of these letters is what we expect it to be, generically speaking. We should also, I was also saying some things about being uniformly distributed, which I haven't mentioned. I haven't captured that idea. Actually, we need something slightly more. It looks the same here, only the difference is I'm considering all of the words W for which this is true for any subword of at least half the length of W. So not only do you get the number of letters you expect in the whole word, but if you look at any fairly large subword, you also get the appropriate distribution of the letters. This is what I mean by uniformly distributed. Or this is enough to prove what I want about uniformly distributed. All right? So not only do you get the appropriate number of AIs in the whole word, but if you look at any of the subwords of long enough length, you also get the appropriate number of AIs in there. All right? This set also has density 1. I call it S epsilon again because it's similar. And I don't actually care at all about the previous one. This is really the one I want to talk about. Actually, it's not. We can improve this very slightly again. We were talking about this lower bound here. Actually, you can get an upper bound by all the same reasons. The statistics on the left side of the distribution are the same as the statistics on the right side of the distribution. So actually, this is a stronger result. The number of AIs in the V you expect to be bigger than this one and less than this one. It's to the middle of the distribution, right? This is statistically what I'm saying here. Okay. This set is density 1 for any epsilon. All right, this is the end of the probability stuff. Now we can just put it all together. This is going to be a very long equations, but every step will be very simple. So I'm going to prove that for each n greater than 1, we have this ratio is equal to 1. Actually, for each n, not in the limit. So there's no dependence on n here, so I'm just going to write e with no n. All right. So first we choose any r and any epsilon. And this is, I'm using a little fact here, but it turns out the expectation when measured across the entire set of homomorphisms is actually greater or equal to the expectation if you only consider maps in this set. This is remnant ratio r and the statistically close to the average, this S epsilon. Rather than considering all maps, we consider only these ones. This is true because we just showed that these sets are both generic. And so the expectation you can just measure on the generic set. All right, this is the definition of the expectation. But this, we talked several times about this ratio is actually greater than or equal to this ratio. And the number of Wagner tails inside the remnant is just equal to the number of AIs inside the remnant. And the total number of Wagner tails is this number of AIs, right? And then we can use the fact that this is in S epsilon. We get those upper bound and lower bounds with the epsilons in them. So it's like this. Then these are constants. We can pull them outside. The ends will cancel. These will come out. And what remains is this ratio of the length of the remnant. But because I assume there's a remnant ratio r, this is actually equal to r. The r also can factor out. And then here I have 1 over this, and then the sum here of 1, this is just going to equal the number of things in the set here. And these fractions will cancel, and the limit will disappear entirely. And we just have this thing here. Remember, this holds for any epsilon and any r. That means, in particular, we can take epsilon arbitrarily close to 1, and r also, epsilon arbitrarily close to 0, and r arbitrarily close to 1. It means that this must actually, well, it means this is greater than or equal to 1, but just by the definition, this ratio is always less than or equal to 1, so it equals 1. This is the lower density, but if the lower density equals, or the lower expectation is 1, then the actual expectation must also be 1. And this is the end. No more proofs. I say obrigado. Thank you for your patience. You also say obrigado for no more proofs. Yeah. What about this? Maybe I'll just return to this for a moment. So the ratio, you can actually show the ratio is expected to be 1 for each n. What about this one? This is harder, like I said before. you know, why is it harder? We use this fact. The Nielsen number, this little guy here, can be the Nielsen number or the minimum number. They must both be stuck between these two values, all right? In a generic situation, these two values on either side are very large, but proportionally they're close together, all right? That is to say, this ratio is close to 1. But the absolute difference between these, because they are going to be very large, the actual difference could also be very large. All right? And that's why this kind of statistical stuff that I was talking about, you can't use the same arguments for the difference as you do for the ratio. So that I'm just trying to give you a feel for what the difference is. So the actual difference can still be quite large, even when the ratio is small. But even so, we are pretty confident that this should be true. So our conjecture is that for any n, we have this. So the expectations should be positive, more than 0 we expect, but also finite. And we also expect this expectation to go to 0 in the limit, just because, I mean, related to the fact that the proportion of beckon maps goes to 0 in the limit. So this is also what we expect to be true. Although this, like I said, the combinatorics is difficult here. Requires fancier counting arguments or fancier statistics. All right, I think that's all. Thank you.
Questions? Somewhere in the middle of the talk, when you construct estimates for density of W2,
Yes.
there are some strange numbers,
Mhm.
0 and 999.
Yeah.
Did you use computer to
No, actually they're very simple. So it's this class T3, which I'm sure you know, is the form of these maps. It looks like the first 2 or 3 letters are specified, and then the rest can be anything. And so the probability actually is easy to measure. I was writing it that way to make it look fancy, but it's some rational number, 1 divided by 21,000 something. It's not a hard computation. Yeah, we used actually the first paper I talked about with the students who came to China, we used computers for that one, but it wasn't necessary.
Any other questions? Then let's thank Chris again.
Thanks.